Welcome to the first of a two-part video training series on filter integrity testing. Filter integrity testing is a routine operation in biopharmaceutical production used to demonstrate that a filter is capable of meeting critical performance criteria such as the ability to sterilize process fluids or injectable final drug product. Reliable integrity testing comes from a good understanding of the test technology and best practices operations. In this video, we'll look at the science behind integrity testing in order to understand what is happening at a micro level. This will provide the foundation for good system design, operations, and troubleshooting. A filter integrity test actually tests all critical pathways between filter upstream and downstream, including seals and device components. But the primary consideration is the membrane. So let's start by looking at the membrane structure and materials and trying to understand what is happening in the pores of the membrane during a test. In the scanning electron micrograph, taking at 4000x magnification, we see membrane filters are a complex structure. It is not like a window screen or a plastic film with little holes poked through it. It's more like a sponge with many openings within the structure to trap whatever we want to filter out of the feed stream. Filters can remove material from the feed by either size exclusion or adsorption. Adsorption retention can be a great way to filter something out of the feed because adsorption can remove particles far smaller than the pore size. But adsorptive forces can be disrupted by pressure or flow variations or by changes to fluid chemistry. If our goal is to sterilize fluid so it can be injected into patients, we don't want to rely on a mechanism that can be disrupted. We instead rely on size exclusion, which works as long as whatever we want to retain does not get any smaller and the pores in the membrane don't get any bigger. So integrity testing is all about assuring the pores have not got any bigger. Key characteristic of polymeric membrane filters is the pore structure is rigid and does not change under process stress due to flow, pressure, or temperature. This makes membranes ideal for critical applications. The best way to determine if a filter can retain something is to challenge the filter with the actual thing you want to remove and evaluate the downstream to see if anything gets through. For sterilizing filters, we use a bacterial retention test. In this test, a suspension of a small organism called Bravundamonas diminuta is prepared and then filtered with the test filter. All the fluid passing through the test filter then goes through a recovery filter. Any organisms that pass through the test filter will be captured on the recovery filter. The recovery filter is then transferred to growth media and incubated. If the test filter is completely retentive, there will be no growth on the recovery filter. In other words, the test filter is proven to be sterilizing grade. The retention test is a fantastic way to see if a filter is sterilizing grade because it's the real deal, it's extreme worst case, and it's very sensitive. Filter manufacturers routinely use the test during membrane development and as a membrane and device QC test. The only problem with the test is the filter gets contaminated with bacteria, which makes it completely unsuitable for an end user's process. What we need for routine testing in a biopharm manufacturing environment is a test that correlates to the bacterial retention test but does not contaminate or alter the membrane in any way. Remember, retention is based on pore size. That's what we want to know. Fortunately, capillary forces are also dependent on pore size, and this gives us a couple options for non-destructive integrity testing. Capillary forces are the result of intermolecular attractions between liquid molecules and each other and between liquid molecules with a contact surface. The measurement of liquid-liquid attractive force is known as surface tension. I can demonstrate by putting water droplets on a very hydrophobic membrane. You see, as the water drops get near each other, they combine. Surface tension is the attractive force pulling the water drops together. The interaction between liquid and contact surface can be seen by putting water on different membrane types. We've seen that water beads up dramatically on the hydrophobic membrane made of the polymer PTFE. The water beads up because it's trying to minimize its contact with the hydrophobic surface. When I put water on a hydrophilic membrane, in this case, a modified PVDF, the water absorbs easily because there is a strong attractive force between water and polymer. The water surface attractive force varies by degree depending on materials. By putting water on another hydrophobic surface, this time unmodified PVDF, we see the water beads up, but not as dramatically as on the PTFE membrane. This shows, although both PTFE and PVDF are hydrophobic, the PTFE is more hydrophobic. The measurement of attractive force between liquid and surface is called contact angle. Surface tension and contact angle are two of the key variables affecting capillary forces. The third key variable is the size of the capillary. In this graphic, the gray represents the polymeric walls of the pore and the blue represents the wetting liquid. The intermolecular attractive forces are holding the water in the pore, and the smaller the diameter of the pore, the more concentrated and stronger the capillary forces. I can demonstrate capillary forces in membranes using these syringe filters, which have membranes with different pore sizes. To start, the membranes are dry, and if I try to put air through them, the air passes with almost no resistance. Next, I completely fill the pores by forcing water through the filter. Now, when I try to push air through the wet filter, there is a lot of resistance. Air does not want to flow through the wet membrane because water held in the pores by capillary forces is a barrier to gas flow. But if I apply enough pressure, I can exceed the capillary forces, push the water out of the pores, and see air bubbles coming out downstream. The pressure required to initiate airflow through the wet membrane is known as the bubble point. The blue filter has a 0.8 micron rated membrane in it. When I use a 0.45 micron membrane, I have to push a lot harder to reach the bubble point. With a 0.22 micron rated membrane, the capillary forces are so strong I can't apply enough force with this syringe even when I push as hard as I can. Because retention and capillary forces are both dependent on pore size, there is a clear correlation between the results of the retention test and the results of the bubble point test. In this graphic, you see the correlation between bubble point and retention. Retention expressed as LRV, or log reduction value. The higher the LRV, the higher the retention. With this correlation, I can demonstrate a filter's retention capability just using clean water and air pressure. There is no fouling or contamination of the membrane. The bubble point is completely non-destructive. In fact, I can repeat the bubble point test on the same filter over and over with no impact to the filter. This correlation is the cornerstone for being able to use the non-destructive capillary forces to assess retention in routine biopharm operations. Bubble point not only gives us a correlation to retention, but it's also a way to identify membrane defects. If I put a hole in my 0.22 micron filter and repeat the bubble point test, I can push air through very easily. The difference between an intact filter and a damaged filter are very clear. In practice, with process scale membrane devices, there are other physical phenomena we have to deal with. When I demonstrated the bubble point with a syringe filter, we didn't see any gas flow at pressures below the bubble point. But at pressure below the bubble point, there actually is a very small flow of gas due to diffusion, which is primarily due to gas solubility in liquid. During an integrity test, at pressure below the bubble point, upstream gas pressure results in gas dissolving in the liquid in the pores. This gas diffuses across the filter to the downstream side. On the downstream side, the pressure is lower, so the gas comes out of solution, resulting in a steady flow of gas. The rate of diffusive gas flow is very small compared to the flow seen when the bubble point is reached, but the larger the membrane area, the higher the diffusive gas flow. The diffusive flow with a syringe demonstration was much too small to see, so when I reached the bubble point, it was very clear. We went from seeing no airflow to seeing bubbles. But with this 10-inch filter, which has a couple thousand times more membrane area than the syringe, at pressure below the bubble point, we can see a steady flow of gas bubbles due to diffusion. How do we know if the flow we're observing is due to diffusion or due to exceeding the bubble point? We can't just look at the bubbles, we have to measure the flow. So with larger area devices, a diffusion test gives us a sensitive method for determining if the bubble point has been reached or not. In other words, a sensitive way to check for defects in larger membrane area devices. Water intrusion, or as we call it, hydrocore, is another way we can use capillary forces to determine membrane integrity. Remember how the water was repelled by the PTFE membrane? That is essentially due to the same variables we saw for the bubble point test: surface tension, contact angle, and pore size. It's just manifested in the opposite way with hydrophobic membranes. In the bubble point test, we measured the pressure required to force water out of a hydrophilic membrane. In the water intrusion test, we measure the pressure required to force water into a hydrophobic membrane. Just like bubble point, the intrusion pressure is correlated to pore size and therefore retention. In practice, we apply water pressure to a point just below the expected intrusion pressure. If there is no water flow at this pressure, we conclude water is not intruding the membrane, which means there are no oversized pores or defects. This concludes our look at the fundamental principles underlying membrane filter integrity testing. We now understand that membranes are rigid, porous structures with a defined pore size distribution, that pore size is the critical attribute relative to bacterial retention, and that capillary forces are also a function of pore size. Once a correlation is established, tests that measure capillary forces allow us to assess retention capabilities quickly and easily and without introducing any contamination. Understanding these fundamental principles will help us perform the test reliably and understand the test results to assure accuracy, and also, in the unlikely event of a test failure, guide us to an understanding of the root cause.